Hello everyone, welcome back to my YouTube channel. I am Manoj PS from Sri Venkateshwara College of Engineering, Bangalore. My USN is 1VE23IS027. I am pursuing my third semester of BE from the Department of Information Science and Engineering. The subject for today's video is data structures. The subject code is BCS304. And the topic for today's video is dynamic hashing and the leftist trees. Dynamic hashing. Dynamic hashing is a technique used in databases and file systems to manage hash tables that grow and shrink dynamically. Unlike static hashing, where the hash table size is fixed and may lead to inefficient space usage or excessive collisions, dynamic hashing adapts to the number of elements stored, providing scalability and improved performance. Let us see the key features of dynamic hashing. Number 1, adjustable size. The table dynamically resizes to accommodate changes in the data set size. Number 2 is minimized collisions. As the table grows or shrinks, collisions are redistributed, ensuring the efficient access. Number 3 is efficient memory usage. Memory is allocated or deallocated as needed, avoiding the data wastage. Number 4 is better for dynamic workloads. It is particularly useful for applications with unpredictable or fluctuating workloads. Let's see the types of dynamic hashing. Number 1, extendable hashing. The directory grows in size as more keys are inserted. It uses a binary representation of the hash value. Only buckets with collisions are split, limiting the overhead. For example, start with a directory of size 1. As keys are added, the directory is expanded and the buckets are split when they overflow. Number 2 is linear hashing. Buckets are split in a linear order regardless of where the overflow occurs. It avoids doubling the directory size, uses a series of hash functions that progressively handles growing data. Example, begin with a small number of buckets. When a bucket overflows, the next bucket in the sequence is split automatically. Let us see the dynamic hashing workflow. Number 1, insertion. A hash function is applied to determine the target bucket. If the bucket is full in extendable hashing, the directory is expanded and the bucket is split. If the bucket is full in linear hashing, the next bucket in the queue sequence is split automatically. Number 2, search. The hash function maps the key to a bucket and the key is searched within the bucket. Number 3 is deletion. The key is removed, and if a bucket becomes underutilized, it may be merged with another bucket to save the space. Here is a pictorial representation of dynamic hashing, data records, and data buckets. Let us see the advantages and disadvantages of dynamic hashing. Advantages: efficient handling of growing datasets, avoids performance degradation due to collisions, and reduces the need for expensive rehashing of the entire table. Disadvantages are it is more complex to implement than static hashing, overhead associated with splitting and merging buckets. Dynamic hashing is widely used in database systems like DB2 and Oracle and file systems requiring scalable and efficient data management. Now let us see the concept of leftist trees. A leftist tree is a type of binary tree designed to efficiently support the merge operation often used in priority queues or heaps. Unlike regular binary trees, leftist trees are structured to favor maintaining a skewed left heavy shape, minimizing the height of the tree's right subtree. Key features of leftist trees. Number 1 is heap property. Like a minimum heap or maximum heap, the value of the root node is either the smallest or largest depending on the context. Leftist property. For any node, the null path length of its left child is greater than or equal to the null path length of its right child. The null path length (NPL) of a node is the length of the shortest path to a null leaf node from that node. This ensures the right subtree remains as light as possible. Efficient merging. The tree structure is optimized for merging two heaps in, unlike binary heaps that require additional arrays or rebalancing. Operations on leftist trees. Number 1 is merge. The fundamental operations in leftist trees. It combines two trees by recursively merging their roots and subtrees, ensuring the leftist property is maintained by swapping left and right children when needed. Number 2 is insertion. It inserts a new element by creating a single node tree and merging it with the existing tree. Number 3 is deletion. It removes the root or minimum value in a minimum heap and merge its left and right subtrees. Number 4 is null path length. It is used to guide trees restructuring during the merges. Example of merge operation. It compares the root values of two trees. The tree with smaller root value becomes the new root that recursively merges its right subtree with the other tree, ensures the leftiest priority by checking and swapping the left and right subtrees if needed. Here is a pictorial representation of the leftiest trees. Let's see the advantages of merge operation. Efficient merge operation in 0 of log n. It is suitable for priority queues or scenarios where merging heaps is common. It is simpler implementation compared to Fibonacci heaps. Disadvantages of leftist trees. It is less efficient than binary heaps for operations like delete minimum or insert when merge operations are rare. It requires maintenance of null path length, adding some overhead. The pictorial representation of the leftiest trees and final leftiest heap. Thank you for watching my video.